Hi, and welcome to the last lecture in our series on synchronization. I am sorry, I had to go back to the Windows platform because this is basically the only computer I have right now. I tried to fix the sound as much as possible. It's not as clear and as clean as the MacBook. I am going to get also for the future. I'm going to get a very good microphone to use for recordings so that the sound is clearer again and better. So today we're going to start talking about semaphores, and semaphores is one of these primitives that are available in most operating systems since the late 60s. Uh, Basically, that provides sort of a more generalized lock. They were invented by Jocastra, who was a Dutch, like Netherlands, computer scientist. He's one of the probably most well-known computer scientists that ever lived on Earth. And it's one of the main synchronization primitives used in Linux and in Unix. And this is basically how Jocastra first envisioned them. How they are implemented is a bit different, and we're going to look at the difference basically. Also, you might look at the number of slides that we have and think that, oh, this is going to be a really long lecture. It's actually not. It's just that there are too many very fast slides that we are going to go through. The semaphores were defined by Jocastra as a positive integer value having two operations. So it's basically it's sort of a data type or a data structure like an int or a long or something of this matter. Uh, but it's always a positive integer type. It has two operations: p, which is an atomic operation that waits for the semaphore to become positive, then decremented by 1. Okay, and this is sort of a wait operation. It's basically used to wait until your semaphore becomes positive, and then decremented by 1 and acquire sort of the lock. And v, which is an atomic operation that increments semaphores by 1 and wakes up a waiting thread at p. So it's basically sort of the signal operation. Basically, once a resource becomes available, then you can call v, basically, which is like a signal, and that signal operation will basically wake up the different callers. And semaphores were actually invented to circumvent the issues we saw with the Mesa semantics for locking uh, or for conditional variables. And so Mesa problems that we saw are supposed, they were the main reason behind Jocastra going through the trouble of inventing a whole new locking mechanism. Jocastra, and we are going to talk about his definition now, defined it as it will never have negative values. So it's an integer with no negative values. This is not what reality is today, but I'm just saying. The only operations are PMV. They cannot read or write semaphore values except at the initialization time. So you cannot basically you can increment, you can decrement, but you cannot read what the semaphore value right now is, and you cannot basically change it. So if suppose the semaphore is 5, you cannot as a p or a v change it to 3, for example, because you're only allowed to decrement by 1 or increment by 1. Operations are atomic. Two p's calls cannot decrement the value below 0. And the sleeping thread at P cannot miss a wake up from V. So it's any sleeping thread will basically always get the wake up from V, never miss it. Okay, so if you look at semaphores from railway analogy, I mean, semaphore, the English word, is basically sort of what you use to signal, right? It's a way of signaling with flags. I mean, there's even a semaphore language where you can use flags to basically signal different letters. And they were used in railways back in the days. That's like 1900s and so on. And the analogy is that if you have, for example, two tracks, like if you look at this figure, you basically have two tracks that two trains can pass in parallel. Of course, when coming out of the tracks, you do not want them to come out simultaneously. So one of them should come out first and then the other one, otherwise they will crash basically. But if you look at this, suppose that you have two stations, one on the top branch and one on the bottom branch, and the trains are basically stopping at these two stations, loading people and so on. So the third train coming from the back cannot go in either of these two branches, so the value is 0. You cannot basically go, right? So this semaphore is initialized for resource control. You can basically have two resources. If there are no trains, then the value will be 2. If one train goes into one of the tracks, then you will have the value of 1. If another train comes to the other track, then you will have the value of 0. And then if a third train shows up, the third train cannot proceed. Okay. Now, these were like the original semaphore definitions that you would find in many operating systems books. And in this case, 3EasyPieces has the actual definition that is used in reality, while many of the operating system books use the definition that was used by the Jocastra in the 60s, which is very far away from the implementation, as you might guess. So the POSIX definition, and here you will understand what are the difference between the two, is that a semaphore is an object with an integer value. So far so good, that we can manipulate with two routines in the POSIX standard. These routines are semaphore wait, which is basically equivalent to your P, right? And semaphore post, which is equivalent to your V. Actually, P and V are the first two letters of two Dutch languages, of two Dutch words that Jocastra used that are very much similar to wait and post. Because of the initial value of the semaphore determines its behavior, before calling any other routine to interact with the semaphore, we must first initialize it to some value. So you should basically, coming to the train example, you have to initialize your semaphore to some value that basically reflects the amount of resources that you have. Okay? So what does this mean? That means that you will have something like this that initializes a semaphore basically using sem_t. This is basically the semaphore definition in C. And you initialize the semaphore to S, and then you basically give a pointer in the initialization when you're initializing. So you created the semaphore, but now you need to initialize the values of the semaphore, and these are basically in this case 0 and 1. This is now called a binary semaphore, where you have only two values, either 0 or 1, in the that the semaphore can well, not only two values, but these are the values that signify the post and the wait in the semaphore. We'll go through them in details now. So semaphore wait will either return right away, okay, because the value of the semaphore was 1 or higher when we call semWait. Basically, semWait decreases the number to 0. It can basically, so you call semaphore wait, the resource is available, you grab the resource, you decrease the semaphore to 0, so now there are no longer resources available, okay? And now threads come in, queue up in your semaphore, they're waiting until basically the semaphore gets to 1 again, okay? And these queued threads will wait until the first thread that acquired the semaphore to basically call post, and when post is called, then the semaphore will be released, the lock will be released, the value for the semaphore will be again 1, and now any thread that basically is able to grab the semaphore will grab the semaphore and will have the will decrement it again. Okay, and again you wake up the threads, all of them. Semaphore post, on the other hand, does not need to wait for anything, because you know that if you have the semaphore, then, well, I have a resource and now I can give away that resource. Okay, and when you call semaphore post, you wake one of the threads. At least one of the threads will get woken up. Okay, here's where the implementation is different from what Jocasta first said. The value of the semaphore can be negative. Okay, and that negative number indicates the number of waiting threads, right? So in reality, what would happen is that the semaphore will not just be 0 or 1. It will be, if the value of the semaphore is 0, then that means that there are no threads waiting for the semaphore to become available. But if the value of the semaphore is -10, then there are 10 threads waiting for that resource to become available. And when semaphore post gets called by the thread that has the semaphore, this value of -10 will be incremented by 1, so it will become -9 once one of the threads acquire the semaphore. Okay, so this is a value that you will not see. You will only see when you're doing kernel hacking, as you have been doing, but it's not something that you can actually read, like how many, like a program cannot read how many threads are waiting on a semaphore.